Hi, my name is Moxey and welcome once again to In the Studio, where we carry on our chat about silicon carbide. We knock down those barriers, we keep on dispelling those myths. And today, yet again, backed by popular demand, I'm joined by our very own Mick Jagger of Silicon Carbide, the Peter Pan of wide bandgap, Mr. John Palmour. Hi, John.
I don't know what to say to that.
Hey, it's all true.
Pleased to meet you. Won't you guess my name?
Right, anyway, getting more serious. So, we've talked about differences of technologies against each other, playing, complementing each other in some ways and being against each other. And then we've also talked about silicon carbide technology of what's coming up, mid-voltage, for example, to give a little taster of technologies that we are driving as Wolfspeed. But let's turn it around a little bit and talk about some emerging markets that could be getting that silicon carbide treatment pretty soon. So again, in our conference world and webinar world, we get a lot of questions about motor drive. When's silicon carbide going to do its due for motor drive? But it's already happening. And when you look around, especially driven by the electrification and mobility, that's a motor drive. Yes, it's got onboard charging, which is excellent for silicon carbide. But that motor drive itself is the biggest item on that BEV. And you've been involved in the automotive space for silicon carbide with the OEMs and tier ones for quite a few years now.
Yep.
And you've seen a lot of transformation. So can you tell us about that journey?
Sure. Well, so first off, I think in the beginning, a lot of people didn't think silicon carbide could really motor drives because
naysayers.
Well, it was more around silicon carbide really excels at high frequency switching.
Oh, yes.
And the motor drive's not a high frequency application. The drives are only 10 to 20 kilohertz. But the big advantage of silicon carbide there is it's a unipolar device, not a bipolar like an IGBT. So there's a certain amount of voltage you have to overcome before you can get any current out of an IGBT.
This being the knee voltage.
The knee voltage. Mm-hmm. So silicon carbide, you start getting current right from the origin. So one of the biggest reasons silicon carbide is winning in the BEV motor drive is conduction losses. So it's not just a switching play, and switching is an important part of the equation.
They have no tail current,
right?
Say.
But actually, silicon carbide has much lower conduction losses, particularly at light load conditions, which is quite often for a variable speed motor drive. So we've been getting a lot of traction in battery electric vehicles because of the efficiency that we can offer with both switching and conduction loss reduction. So, but one thing that's driving the battery electric vehicle market so much is there's a very quantifiable savings right up front, and that is the reduction of the battery pack and or the ability to go to longer ranges for a given battery pack.
Finite energy source.
Exactly,
yes.
Finite energy source. So there's an upfront economic value to silicon carbide because you're carrying your power with you in a vehicle.
On your back, basically.
On your back.
Yeah.
And that's really what's driving it. But as you said, it's just a motor drive like any other motor drive, but it is more efficient. And it's being adopted there because you have this portable power source. But I guess, the next question would be, when is the market going to really acknowledge that same benefit in industrial motor drives?
Yeah, it's certainly a different context because you're absolutely spot on, and I love the way you said it. Silicon carbide is raring to go straight out the box. It's like this wild thing that's ready to go, whereas IGBTs is a little bit fat and lazy until it gets to doing some heavy lifting. But you're right, in a BEV, whether it's a car or a bus, or more so in a bus actually as well, is more the mission profile, isn't it? I think you guys call it. Is far more heavily weighted towards going slow, stopping, mid-power. Unless you're driving the car like you've stolen in it, you're not going to be hitting full power much of the time, which is where IGBTs actually start saying hi.
Yep.
The rest of the time is below that, no knee voltage, lower switching loss. So yeah, I mean, just in percentages, is there any sort of percentages that the OEMs are finding between silicon carbide drives and IGBT-based drives on cars?
So in terms of percentage, at full load, silicon carbide offers about a 40% reduction in losses.
So even at full load?
Even at full load.
When you've stolen it and you're gunning it away?
When you've stolen
Yep.
it, there's already a 40% savings. But when you go to light load conditions, which is where you are most of the time where you're driving, it's about a 70% reduction in losses.
But losses don't equate to actual efficiency, do
No,
they?
they don't. So all of these motor drives are relatively efficient. You still got to do the work. You still got to push the car down the road. So what that 40% at full load, 70% at light load translates to over a driving cycle is somewhere, depending on the bus voltage and the design, somewhere between 5 and 10% overall efficiency improvement.
5 to 10% depends on range, but that's 5 to 10% smaller battery for the same overall miles, or 5 to 10% more range for the same size of battery.
Exactly.
So either way you cut it, if your government's incentivizing EV purchasing for range, we tick that box.
Yep.
Or obviously if you're designing for cost, and of course, if you reduce a battery costs a lot more than a piece of silicon carbide does.
Yes.
And of course, the size of it shrinks down. You're making a much more cost-effective, lighter, better BEV.
Absolutely, and the battery pack is the most expensive part of a BEV. So shaving cost off of that is a big deal. And there's two big concerns about battery electric vehicles. One is upfront cost, so you can address that. The other one is range anxiety, so you can address that. And different companies are balancing those differently.
Yeah, so that's 5 miles. 5 miles that count for sure when you're running out of juice. But I think also anxiety-wise around BEVs is, have we got the parts?
We've got the parts.
There's going to be, what is it, like 30 million BEVs made within the next decade per year, or something huge of that nature, which is fantastic.
That would be, dramatic growth from where we're at today. So, there are some studies saying that 30 million BEVs will be fielded on the road, I think, in 2030.
Which is not that far away.
It's not that far away. It's a much smaller part of the market today, but with all of the focus on a greener economy and climate change, there's a lot of incentives being placed. There's a lot of pressure on the standard automotive, companies, established ones, to really move heavily into battery electric to bring down the emissions from their overall profile.
Okay. Well, I mean, you mentioned, we got heavily into BEVs because we're right excited about that subject, and obviously silicon carbide is really stunning in that.
Yep.
But part of the original chat was industrial drives.
Yep.
So, it's interesting to see the differences in the two applications and how they're going to work.
Well, they're not too dissimilar. As we said, the difference is in the BEV, you're carrying your power on your back, whereas an industrial drive, you're dealing with an effectively, infinite source of power being brought into your factory or whatever. So they look more at that we don't have the cell of the battery pack, but we do have the cell of the overall efficiency.
Yeah.
And because we are getting into the BEV market and this large increase in capacity is going to be required, that's going to drive costs down. And
Economy of scale.
Because we have scale.
Absolutely.
So the more scale we get, the more affordable silicon carbide is. And I think that is what's going to allow us to start penetrating the industrial drive market.
I think it's definitely going to obviously help, of course, but IGBTs is pretty well entrenched in that market. We talked before about 42 years of using IGBTs, classic example. But, we've done a lot of study into this because it is the $2.5 billion question, because right now, according to whichever market report you look at, it's couple of $3 billion of IGBTs go into industrial drives.
Absolutely.
every year.
Yep.
And what was it? Was it 40% of all energy goes through a motor?
40% of energy consumed goes to what's called motion control. But yeah, that's motors.
Yeah.
So moving one thing from here to there, or exerting energy on something in some way.
And we talked last time about how silicon carbide's really making an impact very soon into grid generation, energy storage, renewables. So, we're solving all the world's problems, so let's get to the ones we can't solve, and we're back to industrial drives. And I think from an apps point of view, you're same as an EV, you're still shoving 15, 20 kilohertz up a motor.
Yep.
You're not shoving 400, 500 megahertz, generally speaking, especially into an induction motor type thing. And IGBTs does a fairly solid job, but as we can see from the slide right behind us, just changing silicon carbide to silicon and vice versa has a huge dramatic effect on either, in similar context, you can have for the same power a much smaller motor and drive and cooling, or for the same form factor, you can go from 30 kilowatts to 50 kilowatts. So we know we're more efficient. We know we're going to be cooler, and we're just generally going to be better. But is it enough?
Yeah.
But what's been very interesting in the last couple of years, for sure, and I'm looking to see how various governmental energy policies and things come through, especially in the last year with a lot of green focus about efficiency standards.
Yes.
And we've witnessed this through the server power supply lifespan.
Dramatic change in server power supplies.
Going from, what was it, energy 80 plus, wasn't it?
Yeah, 80 plus.
From I can't remember, one standard to another standard.
Yeah.
And how it's forced the adoption of silicon.
Yeah, but most power supplies, 20 years ago were in the range of about 75% efficient, and then there was 80 plus, and then 85 and 90, and now the titanium standards. But it's had a dramatic impact on the amount of wasted energy in that in a data center.
Yeah,
and and now that there's so much focus on climate change, and again, 40% of all electricity goes to motor control. I think it's inevitable there's going to be tougher, standards on efficiency.
There's got to be.
For these motor drives. And I think you have some information, more than I do on what those regulations are today, but I think that there's only going to be increased focus on that.
Yeah, I mean, we're trying to pick through them, and I don't know, gigawatts to terawatts. What's above terawatts?
Petawatts?
Is it? I don't know. But whatever it is, squillions of watts are obviously going to be through motors. So you're absolutely right. It's got to be addressed. And what we've seen is there are efficiency standards like there are in power supplies. They're not necessarily law, but they are highly recommended legislation.
Yeah.
And each time we go through a particular standard and move to a next one, in motors, for example, it's roughly about 20% lower loss.
Yep.
Each time we jump from one standard to another. And you can see from the slide behind us how these standards are being adopted across the planet. And when we get to today's standard and tomorrow's standard in particular, we're asking ourselves, can IGBTs cut it? Yes, you can throw more silicon, throw more IGBT at something. But it gets to a point where even doing that either becomes too big or too expensive.
Exactly.
So, when we get asked the question, when's SiC going to do its due to motor drives, I think we are seeing that early adoption coming in due to legislation and efficiency standards and the fact that they know we do a better job side by side.
And in particular, I would ask you about, the other thing we offer is, of course, size reduction. So what is the role of silicon carbide, or do you think silicon carbide enters into kind of more the embedded drive market first?
Yeah, I mean, it's a classic case of big is not better every time. And okay, we can be more efficient. Where you have to be more efficient, we can certainly be move-in ready there. But if you're in a drive that's in a factory, it's in a cabinet stuck on a wall, you're not at a real losing sleep over space. But I like the way you said it, embedded, because a lot of drives are not just on their own, they are embedded into fans, pumps, HVAC systems, sorry. Classic example is servo drives.
Yeah.
Pretty much every servo drive is embedded into a machine.
Into a robotic arm of some sort.
Even better, that's the dream scenario, where not only a weight, but size and efficiency is critical. So it does make sense that if you add up being more efficient, being more cost effective, coming onto the horizon with economy of scale driven by electrification, and also being 30 to 40% improvement in power density, then yeah, it wouldn't be beyond reasonable doubt to assume, and we are seeing that silicon carbide is getting entrance into more the embedded space, but today's embedded is tomorrow's normal.
Of course.
So we absolutely think that this is a march forward into that $2.5 billion question. Is it going to be overnight? No. But certainly it's going to be chipping away with a very big ice pick at that iceberg.
Yep.
So, let's watch this space really, and combine that with effects on, grid tying to all these motors. We talked about that before and the enabling of that. We know that, other wide bandgap is not really high voltage, high power, this sort of space. So we're not being congested and fighting and scrapping over that. We know IGBT, although done a great job, is a bit fat and a bit tired.
Yep.
So I'm really quite excited about this possibility.
So we've talked about the drive itself, but all of these big industrial drives can really sap the grid or the power in a building if they don't have power factor correction. So when you turn on that huge inductive load, right, it's going to throw off power factor. So they all have to have some sort of active front end on it to manage that. So what would silicon carbide's role be in that part of the application?
Yeah, superb question, and it's our DNA is from PFC. For silicon carbide. We know that from power supply, single phase stuff. But you're right. And we talked about grid resilience before. So if all these big drives are being switched on, it's going to put a hell of a burden on that grid. So, the passive PFCs, pretty entrenched in the market. But when you move to an active PFC, a 6-switch, 3-phase AC to DC bridge, then it's just the same principles that we see in every other AC to DC converter, whether it's single phase or 3-phase. We see them at 2 kilowatts for server power supply. We see them at 6.6 to 11 to 22 kilowatts in onboard charging. We see them at 20 to 50 kilowatts. Now we're getting more motor drive-ish, aren't we? That 20 to 50 kilowatts for offboard charging. And those against IGBT, and this brings us back to our first conversation, didn't it? The first session. If we can switch 3 to 4x the speed of IGBT, which we can, with no compromise of efficiency whatsoever, those input filters come right down, not only in cost, but size. So again, that big goes to this big. Efficiency is actually 1 to 2% more, and system cost is lower. So I'm really happy that more active front ends are coming into vogue. And bring it on.
Yeah, and again, that's immediate cost savings. That we may not get so much on the drive side, but there is system level efficiencies absolutely on that active front end.
Certainly is. Boom, it's there. And then on the drive, and then yes, there is, I'm sure, work to do on the motor itself. A motor has its inefficiencies, and the motor design community is doing a lot of work there. And obviously we talked about the speed of silicon carbide. So it has very fast dV by dTs. So that's got to be incorporated into the motor system, on the insulation, on the windings, on the bearings. But they've conquered that in BEVs. Silicon Carbide's turning electric motors in cars, so it's not beyond the scope of technology to do. So yeah, I'm very excited, and you can see with the Wolfspeed portfolio of modules and Wolf packs that it's moving focus to these areas.
So what do you think of higher frequency drives? There's certainly going to be some at least niche markets where you could design a higher frequency drive for space savings, et cetera. But there's also a lot of issues with going up in frequency in terms of the load it puts on the bearings and noise and all of that.
Certainly
But where do you see frequency impacting industrial motor drives?
Yeah, really spot on question. And obviously, you just mentioned a lot of mechanical considerations,
yeah.
But that's beyond, my area of expertise. But what I think about is obviously audible frequencies. Mm-hmm. No one likes to hear that whine.
No.
And if you go above 13, 14, 15 kilohertz, you're moving out of the audible, which is a big positive. Yeah, there are, we in marketing call it boutique applications, niche applications for dedicated high frequency. But we show on a daily basis what frequency hard switch, because this is hard switch generally, that silicon carbide can take you hard switch, you're up into the sort of up to 100 kilohertz or so. Resonant, if you can soft switch a motor drive, then obviously you're up into 200, 300, 400 kilohertz. So we absolutely have the capability to service a drive for high frequency. There are some applications already we see, but yeah, they are very specialist.
Yeah.
And it would be interesting to see in general purpose how frequency above audible does really start coming in, if and when it does, or is it going to be okay at 18 kilohertz, and we go forward from there? We just create less loss doing it at 18 kilohertz.
Absolutely.
So, it is a huge question. Time's going to tell, but we're certainly seeing activity and interest around the embedded drive. So let's watch this space, really.
Okay.
So once again, John, pleasure to have you.
Pleasure to be here.
I've learned a lot. You've had a good chat, and hopefully our listeners have been very well educated.
It's been fun.
And once again, please put your questions on our Power Forum. Go on our websites, our Knowledge Center. We have reference designs, we have white papers, application notes, all to try and aid the education of silicon carbide. And to be quite honest, I think, due to the stampede of demand, we'll be back again in the studio. Please join us next time. See you soon.